Hi, today we will learn what axial forces could cause what type of stresses and what kind of deformation happen in a structure. Hi, today we will learn what axial forces could cause what type of stresses and what kind of deformation happen in a structure. For today's lesson, we look at four contents altogether. The first one is terminology, vocabulary per se. What do we use the word to mean anything, right, in this calculation? Then we look at the stress-strain diagram. It provides us with two key elements. One, it provides a linkage between the internal force to the deformation. It also provides us with a key variable, which we call the modulus of elasticity. Then, from those relationships, we will use that to prove our formulation on how to calculate the stress and, of course, the deformation. And here we show one quick example to see how we actually apply those calculations. Before we go any further, I would like to draw your attention to how we call things involving this calculation, or what we call terminology. The first thing I want to say is about cross-section area, right? Imagine this, I still have the two rubbers I used before, right? Now, if we talk about kind of like a structure, a member, right, that we pull apart, we try to pull, this is axial force, correct, in the line of the alignment of the member, we either pull it or press it, right? This area you see right here is not what cross-section area we're going to refer to. Cross-section area we talk about is about, imagine this one here, if there's a line here, you cut through the line and you turn the sideways to see the cross-sectional area, right? I have the broken rubber, which can I use it? Right. So this is the front view you see, correct? Now, if you want to see the cross-section area, what we talk is about separate this one out and then look at it this way, into the side, into the cross-section. This is a cross-section area here, okay? So when we talk about the capital A, which means the cross-section area in this calculation, this is the area we talk about, not this area, okay? The second part is what we're going to talk is about the axial forces, right? Again, notice that when we pull it from apart, this is action force and this is action force. We pull it, right? This is not really internal force yet, because internal force is about what we call axial force, right? In the previous lessons, we already learned how to calculate internal force. So don't forget this. When we calculate stress or even deformation, the capital N we use in those equations, or the force we use in those equations, will be the internal force, in this case axial force, not the applied force. In this case, it would be equal. In many cases, they are not. So be very careful. This last one that we want to talk about is about deformation. In axial force type deformation, then you already have two possibilities, right? One is this one here, right? In tension, then it's become longer, right? Everything become longer. So the deformation is lengthened, right? Become long or longer. Or if it's in compression, then it shrink, right? It becomes shorter. It's shortened or shrink, right? There is no other deformation in this type of direct type to axial force apart from this. I mean the member, not the whole structure itself though. In general, what we want to use in engineering is certain formulation that actually are certain values that can represent all calculation involving a material, right? This is the same thing, right? We're talking about, we want to know how the force affect the deformation, right? So imagine this, we know that if I pull this rubber, right? At the beginning, I can pull it light and it's become long, a little bit longer. That's not hard. And then I keep pulling it, I have to put in more forces and more forces, right? so that it becomes longer and longer. It's up to one point, unless it breaks, then I cannot pull it anymore because it's more than my force can pull it, right? Compression is the same. If I press it little, then you see these two lines here, right? It represents how much the cross-section move apart, right? This is more and more, right? This is shorten and shorten, right? So we want to know how much is effect. Could it be one effect or some kind of one relationship? And then we can use that for all calculation we have. So what we tested in general, let's get the idea, right? So if this is become this one, right? I have another rubber here, right? The same brand, I think. Then I pour it, but it has different cross-section area, right? When I pour it, it's easier to pull, right? Imagine this. So if we draw a graph, we'll find that with the same force, right? The elongation, the change in the length, how much is longer, rely on the cross-section area. The higher the cross-section area, you need more force, and the lower the cross-section area, you need less force, right? So they think maybe it could be not the force per change in length, maybe it's the force per area, right? So the internal force, again, we are talking about internal force here. So they said, well, let's talk about a new variable called stress, right? Which is the symbol we use usually for the normal stress. In this case, as I said, it's normal stress or axial stress. It's usually using the sigma, capital, the Greek sigma, right? The little lowercase sigma to notate it. And it's average all over the area. So it's they try average over the area. So they use N over A, right? And they draw a graph. It fits perfectly well, right? You can change the cross-section area. You can change the shape of it, but then it's a function. It become kind of like the same graph for it. However, they realized one thing though. Imagine that if it has the same cross-section area here, right, like this. If it's long, it is quite long, it's easy to pull, right? Whereas if it's shorter, it becomes in fact harder to pull, right? You notice that, right? So basically, they also find out that the shorter the material become, you need more force to actually change the length in the same amount, right? So they thought maybe it's not the change in length as an absolute. That is actually what we're concerned about. Maybe it's a ratio between the change in length and the original length, or basically delta L over L, right? This is something that we call engineering strain. I have to emphasize the fact that this is called engineering strain because there are some other way to calculate the strain with more or less accurate in other sense, right? But anyway, let's stick with now with the engineering strain. So that will be epsilon. The symbol is epsilon. We use the change in length divided by the original length, right? Therefore, it's length over length. There is no dimension here, right? And now when they pour it, they find out that the whole thing is becoming the same graph, right? But again, this is only when you pour it to a certain amount, not to breaking, right? So they have this graph, the nice graph, the same curve all the time, and this become what we call the stress strain curve, and it's quite consistent for one material, right? If we pour it further in a test or something like that, and we pour it until break, then we have a graph, a full graph like this. I believe you're going to study further in the textbook because there are a lot of written, but then we can separate into different zones: elastic zone, the yielding, and the hardening zone. In this course, we only stick with the elastic zone. Notice that there is a relationship between the stress and strain and a straight line function, right? And of course, we define that relationship as a straight line function starting at 0, 0. Then the slope will be defining that relationship, right? And that slope is a property of a material. The same material will have very similar slope, this one, right? And we call this one the modulus of elasticity, or sometimes called elastic modulus. The capital E letter is donated to it. We usually use that. For the cell argument, let's start off with a bitterly structure. Right? For example, this is a kind of almost a cone shape, and there's a distributed force, which is a function of a distance it moves. And because of the shape, you should realize that it doesn't have a consistent cross-section area either. So there will be two forces pulling it, and there are distributed forces pulling along the length of this beam per se, right, of this structure. And of course, if the original length is L, after this pull, then we presume that it will become longer, meaning we have delta in the chain of the length. So original length is L, one is its pull, and everything is settled. It becomes L plus delta. To analyze something like this, we begin with the small element within that structure. In this case, I will draw a little yellow element in this structure, right, at an arbitrary distance x with a thickness of very small length of dx, right, and I separate that picture out into that smaller free body diagram, right. When now, because we separate the material, the force which you see now is no longer external force, it's the internal force, right, the axial force in fact, right. And because the original length in this small element is dx, and of course it changed after being pulled like that by the 2 nx. The nx denote the change with the length with the position x, right? And of course the length change from the x into the x plus d delta. So if it's small enough, well, and usually we talk in terms of the calculus, it's small enough already. So we could say that the stress at that point, sigma, is equal to n at that point, divided by the area of that at that point, cross-sectional area of that point. Don't forget, it's cross-section area, not the area you see here. You have to look to the side view, right? And of course, the elongation, the strain, is d delta by dx. Right, the change in length divided by original length of that small element, the small yellow element. Right. We also talk about Hooke's law, that there is a relationship between sigma and the stress and the strain. So if we substitute for it, then this is we have. Then because we are solving for elongation, so we should rearrange the equation so that the delta is on one side and the rest on the other, like so. Right, and now if we want the whole thing, we use integration form, right, from 0 to the whole length L. There we are. So this is a general form, meaning if you don't have consistent force, you don't have the consistent axial force, you don't have consistent area, cross-sectional area, this is the integration you have to go through. However, in most cases, what we have is a huge section of our structure might have the same area, cross-sectional area, and the same axial force, or well, close enough, as I already discussed in earlier lectures, right? So in that case, we can presume that n is a constant in that length, and then a cross-sectional area is also a constant, which reduces our form into this nice little equation. The change in length is equal to the axial force times the length divided by cross-sectional area and divided by the modulus of elasticity. Again, that n is axial force, not applied force. A is not the area you see in the front. A is the cross-sectional area, which means you have to look into the side to see it. Okay. So that's the equation we used in general. Now, we have the equation we can use. So let's look at an example on how to analyze for stress and deformation under axial forces. Right. This is a kind of a beam, right? There are 4 forces acting on it, right? There are 2 cross-sectional area, right? From A to B and from B to C are different, and they are also made of different materials, as indicated in the question. So the question is this: what are the stresses between A and B, and what are the stresses between B and C, right? And what is the movement? Not the word. It's the movement of point B and the movement of point C. How much does it move, right? So let's continue. Don't forget that the equation delta we have is for the change in length, not the movement of a point. So there must be a way to link them together, right? But anyway, let's see what we're going to do with it. So from the question, I think it's simpler to calculate the area first so that we get something over with, and our equation when we calculate for the stress and elongation is not too long, right? Okay, so I separate the calculation for the area as such. And then let's look at this thing. As I mentioned before, we need axial force. But in this case, if we look carefully, we don't really need the reaction at point A because we can cut the structure and look to the right hand side of the picture instead. So that's what I would do. The first picture is something I will cut between, mark the word, it's not point B. I cut between B and C somewhere, right? So the distance I cut is less than 0.8 meter from point C, right? So what I will see is the point load, the acting load, 4 meganewton, and the internal force of NBC, right? By this look, I mean, you can see, and I think you can tell there will be no shear if the structure is considered weightless, or the weight is too small to consider, right? So there will be no shear and no bending moment, which means that we can come easily that sigma fx gives you the value of the axial force. We have the equation for sigma and for delta. So it's as simple as that. We just put the equation in, and that's the right. For the stress, we can answer straight away. By the picture, you can see is tension, right, according to the direction of the axial force. Now, because it's in tension, then the change in length will be longer. It's going to extend, not shrinkage or shorten, right? So the delta between B and C is extended. The next picture is I will cut between point A and B, but once I cut it, I will draw from that point all the way through to point C, right, to avoid too many internal force, like that, yeah? So it appears I have, and then I can calculate the axial force between A and B. Notice this time here, it doesn't actually equal to any external force, right? And by direction is compression, but then we calculate stress, then therefore the stress is compression. And of course, the delta this time, because the section was under compression, therefore it becomes shorter than before. But extend and shorter is not what the question asks. The question asks for the movement of point B. That's why we didn't answer them. So we go further a little bit more. Look at the geometry, right? Now, because point A is fixed by the fixed support, right? For A and B to be able to become shorter or shrinkage, it means that point B has to move toward point A because point A cannot move, right? Therefore, the formulation will be in relative term, that's delta B equal to delta A, which is of course 0, and then plus the change that the length has to be. And we can conclude that delta B has to move to the left with the amount we calculated, right? Now, similar idea, point C and point B is moving relative to each other, right? So the movement, total movement of point C will equal to the movement of point B, meaning it moved together with point B first, and then it changed the length. In this case, it did actually shrink. Is extend, which means it moved to the right hand side, right? But because we said that left hand side positive, therefore moving to the right hand side become negative. But when you all sum in the map, it shows that the movement of point C in absolute term is still moving to the left hand side. And then we can answer these two as the answer. To conclude the lesson for today, there are two specific points I want to stress so that we keep in mind of what we have learned today. The first thing we learn is about the stress strain diagram and the importance of the value what we symbolize E, which is the modulus of elasticity, or sometimes called elastic modulus, sometimes it's called Young modulus, right? Which is the ratio between the stress and the strain that is consistent within the elastic region of the stress strain diagram. The second point I'd like to make very strongly here is that to calculate this type of stresses and the change in length, right, you need axial forces, not external force, right? Internal force may be caused, not maybe, is caused by external force, correct? But it's the value you need in calculation is always the internal force, and in this case, the stress, the axial stress, or sometimes called normal stress, and the change in length that is caused by axial force, of course, must be substituted into equation using axial force, not external force. It has been marvelous to have you here. Thank you for attending our classes. Thank you very much, and I will see you in the next class. Thank you.